How is everyone this morning?
Good. How about you?
I'm doing all right.
Nice.
Hey, good morning.
Morning. All right. Any questions before we get started? All right, then. Today, what I'm going to do is walk you through an analysis for doing two-way analysis of ANOVA that is replicated, two-way analysis of variance that is unreplicated, and I want to show you some things about how to treat random effects versus fixed effects. So we're going to spend all this hour in R. Hold on, I need to make sure that I'm recording this. Give me a minute. Okay, we are recording. All right. So can everybody see my R script, my R window?
Yes.
Okay. All right, so as always, the first thing that I do is I check to make sure that I'm in the right place using Git working directory. And so I am in my R script section on my computer. My advice for you guys is you might want to pull this up on your own computer. This script and the data files that are in the script are in the Moodle site. So the first thing that I'm going to do is load what seems like an insane number of packages, some of which you might or might not have. Really, the critical ones that you need is CAR, ggplot, multcomp, RMISC, and LME4 for now. So this first analysis deals with the rat fat data that you've hopefully already played around with a little bit working by hand. So we will get those data in, and it's a small enough data set that you can actually just have it show you the entire data set. So we have fresh fat being served to males and females, and rancid fat being served to males and females, and we have the growth values here. And I have growth, and then I have growth 2. Growth 2 is just where I shifted the treatments around so that I could illustrate what an interaction looks like. So we'll actually analyze both of these and just change the column that we're analyzing. So the first thing that I want to do always is make sure that R is reading my columns correctly. So the first column should be a factor, the second column should be a factor, and then the last two columns should be integers referring to growth. I always like to look at my data first just to kind of get a feel for what it is. So this is a summary SE statement where I'm looking at the data in the data file DAT. I'm looking at the measured variable, which is growth, and I'm looking at how that growth is distributed across fat and sex. And so when I do this, it will give me a table of means. And from this table of means, it looks like fresh fat gives you higher means than rancid fat. And there aren't really many differences between males and females, except that generally males are slightly bigger than females. But The next thing we can do is we can look at the ANOVA with interaction. Since both of these things are fixed effects, we don't have to do anything special. There are only two fat types that we would be interested in, and there are only two sexes in rats. So we can just do an analysis of variance. Now, one of the things that you'll notice about line 36 here is that I'm using linear models. So up to this point, we've always used the function AOV, which stands for analysis of variance. But you can also do this with linear models. An analysis of variance is just one specific type of a general group of statistical models called linear models. And so you can analyze it either way, but how you get the output varies. So I'm going to just go ahead and run this, and then I'll show you what I'm talking about. So when you run this line, you get the command prompt returned to you down here in the console. But when you type summary analysis, you'll see that it gives you a bunch of stuff that you may or may not find useful. And so it gives you p-values for these things, but it doesn't give you a traditional ANOVA table. And it's because you just asked it to summarize the linear model. Well, all linear models are basically like the equation of a line, y equals mx plus b. B in this case is the intercept. M, so y equals mx plus b, m is the slope. And so you can describe a analysis of variance as basically having an intercept, which in this case is 642. That should be the overall grand mean of the grand mean of all of your samples together. So that's the intercept. And then rancid fat lowers that value by some amount, minus 125 on average. And being male raises it by 53. And then there's this interaction between the two that lowers it slightly. And so you can think of this as a line where it has an intercept and it has three slope values: a slope value for fat type, a slope value for sex, and a slope value for the intercept. So that's certainly one way of thinking about an analysis of variance. But the way you've been thinking about analysis of variance is with an analysis of variance table. If you want linear models to return to you an analysis of variance table, you have to ask it for summary.AOV. And when you do this, you will see that it gives you a traditional analysis of variance table. So now that we've generated an analysis of variance table, do you have any questions on how we got here so far? I realize that I just blazed through that lightning fast.
In this case, in this case, what are the variables and what is the question of the data set?
So this is the RATFAT data set. So this is the data set that is in the PowerPoints that we went through. The first example of the two-way ANOVA. Let me go. Give me a minute, I'm pulling it up. So go back to this PowerPoint, the original PowerPoint that we started with, looking at two-way ANOVAs. And this first data set was the RATFAT data set. So this is it. The question was, what's the effect of fat type on rat growth across both males and females? And the question is just, does the type of fat that you feed rats affect their growth? And does that effect vary by males and females? And so this is just the first example that we worked in the two-way ANOVA. Is that what you wanted to know, Athos?
Yeah, and so the R script is comparing data from where, like the Excel sheet. Oh yeah. Okay.
It's these data right here.
Okay.
These are the data that are in that data file.
And the difference of is the fat type. Okay.
So let's go back to the R script. So let's go back up here. So this is just that same data file. It's just in a different form, because rather than being in a table, it's just in 3 columns: fresh fat versus rancid fat, males versus females, and then these are the same numbers that you saw a minute ago in the growth column. Here is the same data that you saw in the PowerPoint a few minutes ago. And if you work through that PowerPoint, you will see that there is a ANOVA table in slide 7, and that ANOVA table in slide 7 should look exactly like this ANOVA table here. And I'm going to go and look at it really quickly so that I can verify that for myself. Sum squares due to fat is 3780.75, which R is rounding to 3781. So that was for sex. For fat, it's 61,204.08. For the interaction, it's 918.75, which R is rounding to 919. And the error or residual sums of squares is 11,667. So it's producing the same ANOVA that we calculated by hand in the PowerPoint. So you have your sums of squares divided by the degrees of freedom. So those sums of squares don't change for both fat, sex, and the interaction. The mean squares are then used. They're all divided by the mean square residual, which gives you these F statistics. The only one that is significant is the fat level. So feeding them rancid versus fresh fat affects growth, but there's no effect of sex and there's no interaction effect. And this makes sense given what we saw when we actually got it to produce for us the means earlier. If we look at fresh fat, much higher means than rancid fat. And so the ANOVA table kind of comports with what we saw in the means. Other questions? Okay, everybody good? All right, then I will press on. So one of the things I want you to understand is what the interaction term does and what an ANOVA does in general. Basically, your data are variable. Everybody's data are variable because there's just variation out in nature. Whether you're dealing with human data or data, relative to rats and what they eat. And so what an analysis of variance tries to do is it tries to basically take this variance and partition it into what things are leading to the variation. And so one form of variation is just randomness that is out there. That's the variation that is in the residual row. And so residual variation is whatever variation is not accounted for by other things. Well, in this case, the other things that can account for variation are differences in the food that the rats were eating, differences among males and females, and the possible interaction between those two factors. anything that is not, any variation that is not explained by fat, by sex, or by the fat by sex interaction is basically unexplained variation, which is what residual variation is. So I want you to compare up here in my R script the difference between line 36, where it has growth, tilde, fat, asterisk, sex. This is indicating that I want it to give us an interaction term. I could have just as easily done it this way, fat plus sex plus a fat by sex interaction. Let me make sure that I wrote that correctly. And it will give us the same analysis that we had before.
Good morning, man. I'm fine with you.
But a shorthand way of doing this is to just do fat asterisk sex, and it gives us the same ANOVA. It means that it's going to include fat as an independent variable, sex as an independent variable, and then it's also going to calculate the interaction for you. Down here on line 43, I have another analysis that I'm calling no int, which is just short for no interaction term. And when I run that, it basically is just fat plus sex without the interaction in there. And when I run that and get that ANOVA table, you will see that the ANOVA table just has fat as an effect and sex as an effect. So what happened to all of the variation that was in the interaction term in the first thing up here? You will see that that 919 sums of squares just got added to the residual sums of squares. So the interaction term doesn't describe a significant amount of variation, but it does describe some variation. It describes 919 sums of squares worth of variation. And if you don't have that in your model, that unexplained variation, variation that's not explained by fat or sex, that variation that is explained by the fat by sex interaction just gets dumped into unexplained variation. Why is it unexplained? Well, it's unexplained because you didn't ask the model to explain it in that way. And so this is now 12,585, which should be 11,667 plus 919. And so analysis of variance is a method of partitioning variation into the various potential causes of that variation. And when you leave one of the potential causes out, the variation associated with that potential cause just goes into residual variation. So what's the problem with not defining, not specifying your statistical model completely in terms of you being able to see differences? This is not a rhetorical question.
Are you ignoring variation between the means by doing that?
No, not really. You're ignoring
Among the means. I'm sorry.
Yeah, I get what you mean. You're not avoiding. You're not ignoring variation among the means. You're ignoring one particular type of variation among the means, the way in which fat and sex interact with one another. But in terms of, for example, being able to evaluate fat, what has happened to the F statistic here? It's actually gone up a little bit.
Yeah, it got bigger, yeah.
So we've got 61,204, and now we've got more sums of squares loaded into the residual, but we also have one more degree of freedom, such that the mean squared actually came down a little bit, which then means that F statistic goes up. That's not usually what's going to happen. It happened in this case because the interaction term was not very large. So it didn't contribute a lot more to residual variation. And it added another degree of freedom, which lowered the mean squared, which raised the F value, which made it even more significant than it was before. But typically, if the interaction term is significant and you don't put it in there, it actually contributes significantly to the sum squares, which raises the mean square residual. What does that do to your F value and your significance level?
It got
If
smaller.
your mean square residual is big, F goes down, which makes it harder to ascertain whether or not that's a significant effect. So generally speaking, by not including all of the potential interactions in your data, you risk inflating the residual sums of squares, the residual mean squares, which then makes all of your F statistics smaller, which makes it more difficult to see differences. There's just more unexplained variation. And we'll see that in stark terms here in a few minutes. It's easier to see it when the interaction is actually significant. Questions? Tukey's test only operates within the analysis of variance way of doing these things. And so to get Tukey's test to compare these things, I've written just another analysis statement, analysis 2. You get the summary of that. It's giving you the same ANOVA table that you had before, but now we can run a Tukey's test on that, and it will tell us what all is different from what. And so you can see that the only significant differences are rancid versus fresh in females, rancid males versus fresh females, fresh males versus rancid females, and then rancid males versus fresh females. So you could, once again, create a graphic that would show what the means are, and then you could label those means with letters indicating which means are different from which other means. We proceeded with this analysis without checking the assumptions. We can check the assumptions by getting the residuals, and it doesn't matter if you get the residuals from the linear model or if you get the residuals from the analysis of variance way of going about doing it. It'll give you the same residuals. Take those residuals, run them through Shapiro-Wilk test. We see that they do not differ from normality, and run a Levine's test on this model, growth determined by fat interacting with sex. And once again, we see that we have a non-significant Levine's test. So everything that we've done is fine in terms of meeting the assumptions of the analysis. Line 65, I have my common formatting block, and then we're going to build a graph. Now, there's some new things in here that I want you to pay attention to. Position dodge is something that you can use so that your data points don't overlap with one another. So whenever you're plotting means like this, you want to leave a little bit of space between the means so that you can actually see the means. So position dodge is just, I just have basically defined PD, labeled this thing PD, used it to define what the position dodge is, and all it does is it jitters the data points apart a little bit so you can actually see the means clearly. Then in the ggplot, we're going to be plotting the data that are in the data frame CI plot. The X variable is going to be fat, the Y variable is going to be growth, and then we're going to color the lines and group the lines by sex. So when you have two different categorical variables, you could have just as easily said that sex was the X variable and that fat is going to be your grouping variable, and it would just flip what the lines are versus what the columns are in the chart. We're going to draw a line, and that line is going to have its position dodged. We're going to put error bars in there, and its position is going to be dodged also. The error bars are growth minus the confidence interval and growth plus the confidence interval. We're going to get points that are also position dodged. They're going to be size 3, shape 21 with a white fill. We could have made this a black fill with a well, now I forget. I'm blinking. Let's just leave it white for now. We're going to give it a X label, which is fat type, a Y label, which is growth. We're going to order these in the order that they will be produced, which is fresh and rancid. And we basically tell it to essentially tell us what the sexes are, female and male, and give them labels that are capitalized is what this thing is. The scale color hue is telling us how we want the grouping variable to be colored. And we want it to be colored by sex, and we want it to be male and female, and we want the labels to be capitalized rather than the way that they appear in the data frame. And then we've given it a title that is the effective fat type on rat growth, and here's the common formatting block. And when we do that, we should get a figure that looks like this. So here you see, in all cases, males are heavier than females, but giving rats fresh fat makes them heavier than giving them rancid fat. Once again, you see really wide variation in these things, but because you only have 3 data points, you don't have a great deal of power to test whether or not these variances are different. So even though you have really wide variances, those wide variances end up being not significantly different from one another because you just lack statistical power to detect them. And so it's dividing the data up by fresh and rancid, and then by sex in terms of the males have a blue line and the females have a red line. Like I said, you could change this so that you can make this X is sex, color is fat, and group is fat, in which case you would have to change some of these things. This would now be sex. This would now be, instead of fresh and rancid, this would be female and male, because R does things in alphabetical order. And this label would now be fat type, and it would be fresh and rancid, and we would do this as fresh and rancid. And assuming that I've changed everything correctly, then it should give us a figure that communicates the same information. It just communicates it in a slightly different way. Once again, we see that females are generally lower than males, and fresh fat, which is in red, is generally giving you higher growth than rancid fat does. Either of these are perfectly valid ways of displaying the data. And it's up to you as to whether you prefer this way or whether you prefer this way. The way you write the figure legend would vary depending on how you plotted it. I generally try and put the x-axis being the factors that I thought were the main focus of the question that a researcher had. And so that's why I began contrasting fresh versus rancid versus contrasting male versus female. But once again, that's more a preference issue rather than a right or wrong issue. Okay. Questions? You guys are so quiet today. Are you all there?
Yep, yep.
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 Okay, all right, just checking. It's a little more difficult to get feedback when I can't see your faces. All right, so the second analysis in this R script is the analysis where I've just basically gone and I flipped these things. So in the first analysis, I just changed the order. I basically moved what was fresh mail, and I put the rancid mail data in the fresh mail category. So I basically took the data that started down here on line 7 of the data file and moved it to line 1, and took the data that was on line 1 and moved it to line 7. What that does is it forces an interaction term to be significant. So it's the same data, I just rearranged them to give you a different view of how things can turn out in an analysis of variance. Once again, we can check all these things again, but we already know that they work because we've already done this. When we do the means on this, now you see that within fresh fat, females are heavier than males, and within rancid fat, females are lighter than males. And so this is kind of the definition of what an interaction is when the response variable is different under one set of conditions than it is under another set of conditions. When we run the analysis of variance on this, what we see now is that the interaction effect is where all of the variation is. So that's where all of the variation in this is. Fat is no longer a significant variable. Sex is no longer a significant variable. Only the interaction is important. But the sums of squares still adds up to the same value that we had before. And once again, this just shows that you can do it with linear models, or you can do it with the AOV function, and it gives you the same result. We can check normality and all that stuff, except it's not going to tell us anything different because it's got all the same data. So let's go and graph CI plot 2, which is the flipped data, and we're going to plot this the same way that we plotted it before. Let me go and get the other plot. Oh, except that I flipped all that stuff around. Now I have to go and change all that. So I want you to see how the plots look different. And you have these plots in the PowerPoint analysis, but let's produce them here. This is the bad thing about doing stuff like this. As we go, you have to sit and watch me type. And that gives us the original data. Yeah, the original graphic. And when we plot this new graphic, what it's going to do is it's going to show us the, oh, crud. All right, so here we have it, what an interaction graph looks like. An interaction graph will have crossing lines as opposed to having roughly parallel lines. And all it's telling you is that males respond differently to than females do to the type of food that they're being given. You give females fresh fat, they grow well. You give them rancid fat, they grow poorly. You give males fresh fat, they grow poorly. You give them rancid fat, and they grow well. It's just basically telling you that the type of fat that you give rats has a different effect in males than it does in females. And that's where that interaction term comes from, is because these lines are now crossing as opposed to not. And so this is the type of plot that you would see where there is no interaction, and this is the type of plot you would see where there is an interaction. Does that make sense? Okay, so let's go back up here to the ANOVA. And so I have this ANOVA table here, which is the interaction. I'm going to add in another analysis. I'm going to make this analysis 5. And in this case, I'm going to get the analysis of variance table, but I'm just going to get it where growth 2 is determined by fat plus sex. So I have left out the interaction term. And when I do this, you see that all of the interaction term in the first ANOVA is now dumped in with the residual variation. So now the residual variation is huge. The residual mean squares went from 1458 to 8097, which means that while fat and sex originally weren't significant, so when you look up here, the p-values are 0.45 and 0.14. Now they are really not significant, because by ignoring that interaction term, all of that unaccounted for variation got dumped into the residual category. It increased your residual sums of squares dramatically. It increased your mean square residual dramatically, which then decreased your two F values. So even though they were non-significant before, they're even more non-significant now. So by getting rid of the interaction term, you significantly reduce, in many cases, your ability to see differences among the means. And so if you have a factorial two-way ANOVA, you should always include the interaction term, because that's generally going to give you a clearer picture of whether or not you have differences and where those differences occur, because it just accounts for variation in your data in a way that is systematic. There's potentially a systematic interaction in your data, and so you should try and quantify that if at all possible. Does that make sense? All right, pull up the unreplicated ANOVA script and the data that goes with it. This is the price data from the markets. So once again, this is the example that is in your ANOVA. This is an unreplicated ANOVA, and so the price data look like this. It's just a bunch of supermarkets, it's a bunch of brands, and it's a bunch of prices. I think in the screencast, I was talking about this being the price of toilet paper, perhaps. In this analysis, because it's an unreplicated analysis, I've told you that we can't do an interaction term. So I've specified this analysis as basically an ANOVA where price is determined by supermarket plus brand, not supermarket asterisk brand. So I've specified it as not having an interaction. So when we run this, it's going to just give us the effect of supermarket and the effect of brand. Both of these effects are significant. You can try and run it with an interaction term included, but R is not going to let you do that. So we specified the interaction term, but it doesn't give us the interaction term. it just gives us supermarket and brand, and it doesn't even give you a full ANOVA table because it knows that you're trying to do something dicey that it's not supposed to do. You can't calculate the interaction term because there is no within supermarket replication in this case. And so, so this correct way to specify this is to know that it's an ANOVA without replication and just use the plus from the beginning, and then it will give you the full ANOVA table. We can get it to give us the means broken down by brand. We can, and so now it says brand A, B, C, and D, and it gives you the mean price. We can also get it to give it to us broken down by brand and supermarket. But one of the things that you'll see when you do this is it just returns the data set to us. And when you do this, you see that it has an NA for standard deviation, standard error, and confidence interval. Because it's an unreplicated design, there is no replication of brand A and supermarket A. So there is no replication that you can calculate variance and things like that for. So all these values don't get calculated because it can't calculate them. So in this case, doing measures of normality and homogeneity of variances is also meaningless because once again, there is no within sample variation. And so we don't typically do those types of checks on the data. And so what we can do now is we can basically just do plots of these things. So we can plot the brands, and this basically shows you that brands B and C are more expensive than brands A and D. We can bust up the data just by supermarkets. So this is the mean of all 4 brands across all 4 brands in supermarket A, the mean across all 4 brands for supermarket B, and we could plot those, and we can see that some supermarkets have higher means than other supermarkets do. This is why supermarket is a significant effect. And then we can also, once again, bust the data up by both supermarket and brand, but that just returns the data set. But we can also plot that. And this is a plot that appeared in your PowerPoint. And because you can't test interactions, a good way of assessing whether or not there are interactions is by looking at this type of a plot. This is probably the easiest way to see interactions. And what you see is that brand B and C are generally higher than brand A and D. Well, we learned that from the brand plot over here. B and C have higher price than A and D. But what we see is that the order of those two things doesn't really change much across the supermarkets, and they're always higher than brand A and D, which are always lower. And in the lower section, brand A is almost always slightly higher than brand D. Because these things are moving in parallel with one another, and you don't get a lot of crossing of lines, you get some, but not a lot, you would say that there probably aren't any interaction effects in this model, because you don't see the lines crossing a lot. And that is an unreplicated analysis of variance in R. And like I said, whenever you have R giving you something incomplete when you expect something complete, like up here, it probably means that you've asked it to do something that R knows it can't do or shouldn't be doing. And so then just go back and specify the correct analysis, because you are a smart statistician and you know that this is an unreplicated two-way design. Questions? You guys are so quiet. I feel like I'm just making a screencast.
I have a question.
Yeah, Grace.
So when you have an unreplicated, this is just to like clarify, when you have an unreplicated data set that you're doing an analysis for, you just do the factor or like the, I don't know, factor plus factor or whatever. But then whenever you are doing one that is replicated, you have to do both the factor plus factor and the factor asterisk factor.
No, you can just specify it. I'll go back to the RATFAT script. You can just do this asterisk.
Okay.
And this is the same thing as doing, I'm going to do this. So I'm going to have to go back and reload the data over here. Yep, okay. So analysis 4 is an interaction, and then analysis 5 was me removing the interaction by just doing fat plus sex. Well, I can go in here and add to this a fat colon sex term. So if I run analysis 4 here, it's going to give me the full ANOVA. If I run analysis 5, it will also give me the full ANOVA. Okay. So you see, this is analysis 4 right here. This is analysis 5 right here. It's given me the same result because I've asked it for the main effect of fat plus the main effect of sex plus the interaction effect. The shorthand way of doing this is just to tell it at the beginning, give me everything. When you put fat asterisk sex, it's asking for the interaction, but you can't have the interaction without having the main effect of fat and the main effect of sex. And so it just automatically calculates all of those things. It doesn't really matter how you write it. It gives you the same answer either way.
Okay.
One of the things you'll discover about R is there are about 12 different ways of doing any particular thing you want to do. And so part of succeeding in R is knowing the way that you prefer, recognizing that other people have other ways, and recognizing what they're doing when they're doing things.
Right.
I'm trying to give you an exposure to, okay, here are a subset of the ways in which you can go about doing this. The two most common ways of doing this, actually. So if you get stuck while you're working on your homework or while you're working on the Gecko analysis, and you see somebody coding it this way, which you will see, people who have written, Stack Exchange answers to questions and tutorials and things like that, just recognize that these two things are equivalent.
Okay.
Other questions? All right. Since there are no other questions about that, I want to go and do some things. If you look in your textbook, in chapter 9, which is where they cover two-way analysis of variance, you will find that there is a data set in box 9.4 and a data set in box 9.5. And what I want you to do for practice is to download these data sets. They are on the Moodle site. One data set is called Quinn. The other data set is called Minch, M-I-N-C-H. And Quinn is the example that is worked out in box 9.4, and Minch is the analysis that is worked out in box 5. Box 4 is a two-way analysis of variance with fixed effects. Box 5 is a two-way analysis of variance worked out with mixed effects, where one effect is a fixed effect and the other effect is, a random effect. Now, you'll find on the internet lots of people saying, giving you advice on how to go about calculating a mixed effect model. My advice is to run it as a fixed effects model and then calculate the F statistics yourself. I've tried lots of people's methods of doing this in other packages, and for me, the easiest thing to do is to run the fixed effects model and then ignore the F statistics in the ANOVA table, and instead refer to table 911 for how you should go about calculating the F statistics. And so just to quickly run through this in the last 10 minutes or so that we have, load up all the libraries. The Quinn analysis, when you import it, it basically has density of these. Let's see, what is Quinn again? I have to go back and look. These are densities of limpets, and it's looking at the density of limpets in spring and summer and the effect that that has on the number of eggs that they produce. And so when you look at the data, you see they have densities of 8, 15, 30, 45, and then they have summer and spring, and then they have the number of eggs produced by these limpets. Now, one of the problems with having numbers as a factor is that when you ask R what class of data that is, it's going to tell you that it's an integer and you actually want it to be a factor. So then you have to tell it to treat density as a factor, and then after that, it will treat density as a factor. Check your other things to make sure that they're factors and that they are numeric data. And so once again, we can get whoa, what happened there? We can get a general look at the data by looking at how many eggs are produced across both density and season, and look at that plot just to make sure that it looks right. And then we can do a two-way ANOVA with an interaction term. I've had a tickle in my nose the last couple of days. I've been sneezing more than normal. So we can get the ANOVA table, and when you look at this ANOVA table, it should look exactly like the ANOVA table in box 4. So you see that the density in box 4 has 3 degrees of freedom with a mean square of 1.76, 3 degrees of freedom with a mean square of 1.76. In the book, it has season with 1 degree of freedom because you only have 2 seasons, spring and summer, with a mean squared of 3.25. The interaction term has 3 degrees of freedom, 3 times 1, and a mean squared of 0.06 in the book, which is 0.055 in R. And density is a significant effect, and season is a significant effect. And the p-values all match up with what is in your textbook. So it looks like R has produced the same analysis that we would produce in this. You can now do a Tukey's test on this if you want, and it will show you all of the possible combinations, and there are a lot of them because you have so many combinations of season and density. But it's really easy to see which ones are significant by just looking at the p-values on the far right. So you can see which of these are actually the significant ones. You can test these things to see if they meet the assumptions. They are normally distributed, and they have no differences in variances. And then you can plot these data. And the plot looks something like this. And so what you see is densities going from 8 to 15 to 30 to 45. As the density goes up, the number of eggs produced goes down. but you generally have more eggs being produced in spring than in summer. And because these lines are all parallel, you should have seen no interaction term. And if we go up to the ANOVA table, you see that there is a significant effect. There's a significant effect of density, meaning that as density goes up, numbers go down. There's a significant effect of season, and that spring is greater than summer, but there is no interaction term. And so once again, the figure is in line with what you found in the overall ANOVA, and that should always be the case. So that's easy, because presumably these densities were densities that they were interested in for a particular reason, and the seasons are the only two seasons that you have to worry about with reproduction, because these things only reproduce during the spring and the summer. The Minch data, the Minchinton and Ross data in box 9.5 is different though, because this is looking at the distribution of oysters as habitat for limpets in a mangrove forest, and they had different zones that are presumably a fixed factor, but then they also had a number of different sites that they looked at, which were just a random selection of all the possible sites where you could find these organisms. And so these are densities, I think, if I recall correctly. So when we load that data file up, we get site, which is a factor, we get zone as a factor, and we get the number of limpets, which is a factor. And so when we look at a breakdown of that, we see that densities are all pretty low, but we have site A and B, and we have these different zones within each site. And so we can define this as, if you go and look for how to do this in R, you will see that you use a program called linear models. And this is how you would specify it. But unfortunately, what it gives you is that this is a singular data set. And all that really means is that you have a bunch of variances that are very close to 0. And as a result, it has trouble calculating the analysis variance, to the point that if you ask it for the analysis of variance, it doesn't return anything to you. So what you should do is you should basically just specify this as a regular analysis of variance. So we're going to go and just, whoa, what happened there? Oh, I know what happened. In the book, they transformed the data. They took the density, they multiplied it times 100, and then took the square root of that. So now there's an extra column out here that actually ends up being this one. I just calculated it myself to make sure that their data set was doing the right thing. So we can then do an analysis on this. And when we do, we get a regular analysis of variance table. But when you look at this analysis of variance table, you're going to see that these values for the F values are different from the F values that are in Quinn and Keogh. And the reason is that we're treating zone as a fixed effect. And in the fixed effect model, if you look at table 911, in the fixed effect model, you divide the fixed effect by the interaction term, whereas in this case, it's dividing the fixed effect by the residual term. And so what you would need to do is copy the sums of squares, the degrees of freedom, the sum of squares, and then the mean squares. And then rather than using the F values that R produces for you, calculate the F values yourself. Divide 13.083 by 10.594, and you will get a F value for zone, which equals 1.24, which is the value that is in your textbook, because you know that site is a random variable and zone is a fixed variable.
So Paul, usually the F value is the mean squared of, say, zone divided by the mean squared of the residual.
Yep.
But now in this case, the difference is the denominator is now mean squared of your interaction term.
Yep,
Okay.
that's exactly right. Yep, and you'll see that in table 911 in your textbook, and that table is also reproduced in the PowerPoint where we talked about fixed versus random effects. So for me, this is the most straightforward way of doing this, and it just requires you to do a little bit of math yourself, because oftentimes the ways in which people have programmed R to do it, they just don't behave well.
So when we're chipping away at this, do you want us to do this? It looks like you've transformed some data. You're going to want us to do that?
I just did the transformation that was in the textbook. The only reason you should ever transform data is when your data are not behaving well in terms of the assumptions that are necessary to run an ANOVA. So if you get a non-significant test for normality and a non-significant test for homogeneity variances, just press on. And sometimes when you do get a significant result for those two tests, you still just want to press on with the raw data. Because when you examine those data more carefully, it's probably a sample size issue that you're looking at, where you're seeing really, really small differences in variance that probably are not of much concern. Does that make sense?
Yeah, thanks.
Yeah. So just ask R for a regular analysis of variance, and then go through and calculate the F's as you know how to calculate the F's, because you know how to deal with fixed and random effects in a mixed effects model. And so in this case, site would be divided, you would take the mean squared of site and divide that by mean squared error, and that would give you the correct F statistic. And then the interaction term is always divided by the residual term. So this would be in figure 9.11. This would be the restricted version of the fixed and the fixed effects, where you divide the fixed effect by the interaction, the random effect by residual, and the interaction effect by residual. So on Wednesday, we will talk about Friedman's test, which is an alternative, non-parametric alternative for doing a unreplicated analysis, two-way analysis of variance. As it turns out, there is no non-parametric equivalent for doing a two-way analysis of variance with replication. So if you don't meet the assumptions, you're just stuck with using a standard two-way ANOVA. So we'll cover that. That's going to be a relatively short thing. I'll post a screencast going through that. We'll answer questions about that on Wednesday. Hopefully, now that you know how to run two-way ANOVAs in R, you will get started on your homework if you haven't already, your problem set if you haven't already. So what we'll do is we'll talk about Friedman's for a short period of time on Wednesday, and then we can spend the rest of the time just troubleshooting what you're doing in terms of problem set.
Okay,
So
sounds good.
that will imply that you've started working on your problem set by then. All right. Well, this has been a very one-way conversation. It feels weird, but hopefully it's working for you.
Hey, Paul, real quick on the Friedman's, you said it's the non-parametric analog to two-way with replication?
No, without replication. There isn't. Yeah,
Okay.
there isn't a non-parametric analog of a two-way ANOVA with replication.
Okay.
At least not one that I am that I am aware of. And somewhere in my office, I have an entire book on non-parametric. Oh, I think it's at my house, an entire book on non-parametric statistics, and they're just, nobody ever invented one.
Yeah. And looking at the Quinn and the Minch stuff, looked like they both were with replication. Is that right?
Those were both with replication. Those are just examples of the difference between two fixed effects and a mixed effects model, where one is a random effect and one is a fixed effect.
Okay. And the random was that zone, whatever that zone thing was.
Random is site. Zone is fixed.
Okay. Okay.
All right.
Okay, good. Thank you.
All right, then I will talk to you guys on Wednesday. And if you have any questions between now and then, just drop me an email.
Okay.
All right.
Good.